All right, so we've been talking about energy. We just want to take a look at pendulums here for a minute. Okay, so pendulum is anything, whether it be stiff lever or string, is something hanging down with something attached to it, and we know that it can go back and forth, right? Kind of a curved path. Okay. And so when it's at its bottom, if it's a pendulum on its own, it's not going to start moving, right? There's really no potential energy here. Unless we cut the string, it would have gravitational potential energy. But assuming this is the bottom, it's really not going to move. Now, if we move it to here, that was not a very good drawing. Okay, let's see here. Let's insert a line actually, or not. Never mind. Okay, we see if I can do this a little better this time. Then there we go. Oh, jeez. All right, cool. So we have our pendulum here now. Okay, we've got it up, so we know that it's got gravitational potential energy, right? Because if you let go of it, it's going to fall downward, right? You've got tension acting towards the top where it's connected to the ceiling, and then gravity's pulling it down. So our net force will cause it to end up going that direction and accelerating, of course. Okay, and so if I let go, it'd go through here and keep going on upwards. It would end up here. All right, so we've got to think about our energy at the different points. Okay, let's color code them for us. And so if we're assuming it's moving down here at the bottom, okay, we know that we just said the gravitational potential really in this system is going to be pretty low based on the string holding it up. Okay, but so in the middle here, all of my energy will be kinetic energy, right? Okay. This is moving, and it's not going to have any potential to move faster in the given situation. So what it's going to do is going to go up, and again, the net force will be going then against it. It'll slow down until it stops at the height of the pendulum's path. So here would be your maximum height, and so now all of your energy will be your gravitational potential, okay? Which is equal to mgh. And here the h would be the difference in height between the bottom and the top. Okay, it'll then go back down and keep changing in between. And so another way to think about a pendulum is like, if you have a rope hanging from a ceiling and someone wants to go be Tarzan, right? They're running at it, they jump on the rope, and it swings up with that person on. Yeah, you can calculate how far it'll go up because if you know mass and we know velocity, the maximum height, like we just showed on this pendulum, our k at the beginning, our initial, will equal our gravitational potential at the end, final, right? Because at the very height, it's kind of like throwing a ball up in the air, right? It goes up, slows down, stops, turns around, and speeds up again. So with the pendulum, it'll go up, eventually reach its maximum height, stop moving, and then fall back down. And so for any question like this, kinetic energy is 1/2 mass times velocity squared. Your gravitational potential energy then would be mgh. Now, if you look at this, you'll note something interesting. Mass does not matter. All right. And so if you've got a 50-kilogram child or a 100-kilogram man running at the same velocity, they will end up going the same height. And all you have to do is use velocity squared. 1/2 velocity squared will equal the height times acceleration due to gravity, which we know here is 10. And so that's just ways to look at pendulums. We know that as it swings, you've got when you pull it up and hold it, it's got maximum gravity. All of its energies in gravitational potential. You let it go, it turns from potential to kinetic. At the very bottom, it's all kinetic energy because it's going to start going up. It's slowing down, losing kinetic energy into potential energy. All right, so you can also take a look at the spring real quick. Okay, you can do one of two things. You can go from spring potential to kinetic, or you can go kinetic to spring potential, right? And so if we were to pull this back, actually, let me collect all this. We can go from kinetic to spring potential, right? And so if we use this like a ping pong ball launcher, and we pull this back to part A here, and let's say C is the zero compression, so there's no compression here. That's C. If we bring it back to A, we know that our potential energy, or spring potential energy, is 1/2 kx squared, or the displacement squared. And once we go from A to C, at C it'll all be kinetic energy. And so it'll be 1/2 times mass of the sphere times velocity squared. Okay. Now we were treating it like a shock absorber instead, and we sent the ball in, the velocity goes in and it hits a spring. Well, if you know the mass of the sphere and you know how fast it's moving when it hits a spring, you can then calculate one of two things. You can either measure the displacement, and then you can get the spring constant from the displacement, right? Because if you know mass, velocity, and displacement, k is the only variable left. If you know the spring constant, instead, you can actually predict the displacement. Okay. And so again, a lot of this energy stuff is thinking about what's happening in the situation. Where does the energy start? Where does it end? How do my equations relate? And then it's just a lot of algebra manipulations. So let me know if you have any questions.